Hello, everyone. Welcome back. Happy Monday. We are in the midst of learning about how to draw root locus diagrams. We have had 1.5 classes so far, but let's go ahead and make a quick review of what we've covered. So this is Unit 5, and we talked about the procedure steps, and what these are basically these glimpses that we get into the lives of where closed loop poles are or can live for certain variable values of k, the open loop gain. And so we talked about that in class number 1 in this unit. We talked about how all those finite points on the plane that attract closed loop poles as k gets large have to be open loop zeros. And the complementary fact there is that all those finite points on the complex plane that emanate closed loop poles for small k are open loop poles. So by and large, the idea is that closed loop poles will migrate from open loop poles to open loop zeros. Now, that would be true if there were an equal number of open loop poles and zeros. If there are a dissimilar number of open loop poles and zeros, then some of the root locus branches, and to review, a branch is the path of a single closed loop pole, have to either start off the page or, more commonly, end up off the page. In class number 2, we talked about all those regions of the real axis that pass the phase criterion. And so those are the portions of the real axis that fall in the root locus, also called loci. And then lastly, on class 2, we talked about a little bit about the behavior of the branches that go, quote unquote, off the page. We called them asymptotes because they behave just like asymptotes for functions. They are directions to which the root locus branches converge as k goes to infinity. Okay, so that leaves us today with class number 3. We're going to start talking about angles of departure and arrival. But after that quick review, are there any questions that have come up? So let's go ahead and move to this page in your note set. So we've seen that every open loop pole, I think a reasonable analogy is gives birth to or emanates a root locus branch. And so far, the only ones that we have been able to determine what that birth looks like is this open loop pole sends a closed loop pole that way, and this open loop pole sends a closed loop pole that way. Now we also figured out that this open loop zero attracts a closed loop pole branch, but we have 3 closed loop pole branches that are really unaccounted for. We know that one of them is going to end up going that way. It's going to follow that asymptote. It's going to follow that asymptote. So we know what they're going to end up, but the question I want to answer now is, where do these other 2 branches begin? And they have to begin somewhere around this pole, and then analogously somewhere around that pole. And so what an angle of departure is, it's simply the angle at which the branch departs this open loop pole. Okay, so is it going to be that way and we get something behavior like that, or is it going to be kind of that way and we get some behavior like that, or even something crazier? We don't, at this point, we don't know how this branch will depart from this open loop pole, and that's the question that we're going to answer rigorously here. So let me clean up the diagram. Our workhorse here is going to be the phase criterion. So recall, the phase criterion says that the phase of the open loop transfer function, when evaluated at any test point that we think is going to be a closed loop pole, has to be plus or minus 180, mod 360. So it has to be 180 degrees. And what we're going to do is we're going to pick this test point and we're going to put it somewhere in the neighborhood of the open loop pole that we're trying to depart. Now the idea is that I want to pick this test point as close as possible to this open loop pole, but not exactly on it, because I need to measure the angle at which we get from this point to that point. That's going to be the crucial angle. So if I'm not telling you exactly where S hat is placed, I'm not giving you a heading or a length, I'm just telling you S hat is near this X, how are we going to compute the constituents in the phase criterion? How are we going to do this computation, which is what angle of K plus angle of S hat plus 2, for the example that we have, minus the sum of the other angles. So this is angle S hat plus 1 plus angle S hat plus 3 plus angle S hat plus 1 plus J plus angle S hat plus 1 minus J. All right, so for the running example, these were the terms we have in our phase computation. So any ideas? Anyone been reading up, actually? That's the real question here. The trouble is that we don't know exactly where S hat is. I mean, we could say it's at -1 plus J plus some epsilon disturbance. But what I don't want to do, I don't want to actually tell you exactly where S hat is because I don't actually know where S hat is. I don't know which of these angles will give me a valid phase criterion. So what I'd like to do is I'd like to make an approximation. I'd like to say that S hat, I don't know exactly where it is, but I know that it's darn close to this X, which means if I were to draw my vectors, not pointing at S hat, but instead pointing at the X, this angle is going to be darn close to that angle, which is the actual angle that I want. In fact, when S hat gets closer, that approximation gets better, until in the limit, when S hat is an infinitesimal distance away from the open loop pole, this is entirely equivalent to the actual angle that I'm after. So I'm going to approximate the angle of L of S hat using these kinds of angles. I'm going to call that gamma 1. So this I'm replacing with gamma 1. And I'm going to keep doing that. I'm going to say, I don't know what this true angle is, so I'm going to approximate it with this angle. I'm going to call that theta 1. And likewise here. So the idea is that I'm approximating these vectors whose tails I know exactly where they ought to be, but whose tips I'm not quite sure. And I'm going to use the only point that I know in this area as my guideline. So this is going to be now theta sub 2. And let's see here. So this is call it theta sub 3. And that's the vector pointing from, I think it's this point, to S hat. Now, the only term for which this process doesn't work is this one, because this is the angle formed between S hat and the actual pole that we're leaving. So I can't do the trick of approximating the vector by rooting it at the open loop pole and pointing it at the pole of departure, because they're the same thing here. But the good news is that this thing is actually exactly what we're after. I'm going to call that the departure angle, right? This angle is actually what we're solving for. Because so far, angle of K is going to be 0. Gamma 1, we can measure it. In this case, it's 45 degrees. Theta 1, we can measure it. It's 90 degrees. Theta 2, we can measure it. It's some arctangent. Theta 3, we can measure it. And theta D is the only unknown, provided that we enforce the phase criterion, provided that these angles all sum to 180 degrees. Any questions on that? So this is the only unknown. Okay, so that's the reasoning behind this slide and the rules presented in this slide. So the idea is that angles of departure are the angles at which branches will depart or leave a complex conjugate open loop pole. And so a couple of caveats here is that this is true when doing calculations in the positive half plane. So let me go back here for a moment. If I get theta d, if I get the true angle of departure up here in the positive half plane, do I have to restart the whole analysis down here? And the answer is no, because the root locus diagram is always symmetric between the positive half plane and the negative half plane, between the top and the bottom. Because the closed loop poles are still roots of a real coefficient polynomial, so they have to be complex conjugates. Therefore, whatever a root locus branch does in the northern hemisphere, its southern hemisphere has to mirror that. Okay, so once I get theta d for the northern hemisphere, then that's going to be the same but mirrored for the southern hemisphere. So these formulas are only for doing your geometry in the northern half plane. And as I used the notation before, these are angles from open loop poles, and these gammas are angles from open loop zeros. So these are departure angle calculations, and they represent the angle measured from the positive real direction, which the root locus branch departs an open loop pole. The analogous quantity over here would be an arrival angle. If we had a complex conjugate open loop 0, then we would want to know at what angle do the branches arrive. I mean, there's no better word for it. At what angle do the branches arrive at the open loop zeros? Okay, and this is the same idea. These are still open loop pole angles, and these are still open loop zero angles. Okay, so let's work out the arithmetic, or I guess the trigonometry, for our running example. So this is the example as we have it so far. We have the center of mass, we have the asymptote angles plotted, we have the real axis loci shaded in, and so now our job is to figure out the angle of departure. So let's go ahead and do that. We have theta d is 180 minus the sum of all the angles from the other poles. So that's 90 here. That's another 90 from this bottom one. And what's that going to be? That's going to be angle whose tangent is rise over run, so 1 on 2. And then we're going to add to that the angle of the vector from the open loop 0 to the pole that we're departing. So this is 45 degrees. Okay, if you get your calculator out and you work out the arctangent of 0.5, this is approximately 18 degrees. Okay, so let's clean up our construction lines here. And I have to now draw a branch that is departing this open loop pole and whose angle formed with this grid line is approximately 18 degrees. Okay, so if we have worked out the angle of departure in the northern half plane, then we're going to mirror that down here in the southern half plane. Okay. So in this case, it looks like the branches are going to depart these complex conjugate open loop poles, and they're just going to gently kind of slide towards these asymptote angles. Okay. It didn't have to be that way. You can also cook up systems in which these guys make a complete 180 and then have to go follow the asymptotes. Any questions on this? Actually, can I get a mic check? Have you all been hearing me? Because you're really quiet.
Yep.
Okay, sweet.
Yep.
It's just so easy, right? There's no questions.
I do have a question.
Okay, go for it.
Where did you get that 45 degrees that you added on at the end when you calculated your approximation?
So that is the gamma, the angle formed by this vector.
Gotcha.
Yeah. Rise of 1, run of 1.
So the 18 degrees is just where it leaves, but then it follows that asymptote?
Good. That's a great point, is that the 18 degrees only applies in this kind of epsilon bubble around the x. It says nothing about what happens in kind of this region or that region or anything else out here. And that's why it's okay to have a departure angle, 18 degrees, that's different than our asymptote angle, which was 60 degrees. Yeah? We know that at very small k, this is going to form an 18-degree angle. At a very large k, the branch is going to form a 60-degree angle. So there has to be some transition between the two. Great question. And the whole departure angle analysis assumed that the test point was very, very close to the open loop pole. So the conclusion we get is only applicable in a neighborhood that's very, very close to the open loop pole that we're departing. Cool. So we're getting a pretty good sense here. Actually, I think it might pay dividends if we take a moment and kind of ask ourselves, like, what have we learned so far? I mean, not in terms of root locus, but in terms of the system. What can you say about this system that you maybe couldn't have said at the beginning of all this? We're not done, so I mean, we'll learn more, but what are some things that jump out at you? How many closed loop poles are there?
4?
That's right. So there are 4 closed loop poles. Maybe you didn't need a root locus diagram to tell you that, but I think it's interesting that if you were to ramp the open loop gain very, very large, 2 of the closed loop poles would be in the right half plane. Can you see that from this diagram? Or does anyone need help seeing that from this diagram?
I need help.
Okay. So for small k, so let's do a piecewise case here. So for small k, we're going to have, and this is small meaning close to 0. We're going to have, let's get some new colors in here. Yeah, sure. For small k, we're going to have closed loop poles kind of roughly here, and roughly here, and roughly here, and roughly here. Okay, and these again are very rough, depending on how small k is. So for very small open loop gains, we're going to have a stable system. We're going to have, do you think this system will behave like a 4th order, like a 3rd order, like a 2nd order, or none of the above?
Well, yes, a 3rd order.
You might say a 3rd order because these kind of 3 poles are all in a line-ish. But remember the psi test, the ratio of real parts. This real part is still only about 3, and this real part is only about 1. So I don't think it passes the dominant pole approximation at all. This is going to be kind of a full-fledged, really confusing 4th order system. So, okay, these are one of the things that I want you to start to see from these root locus diagrams, that they're not just pretty pictures, they're actually ways to tie together pretty much everything we've learned so far. So for small k, we've got 4 stable closed loop poles. None of them really dominate anyone else, and so this is going to be pretty hard to analyze. Now what happens if we make k larger? Let's do orange. So as k gets very, very big, well, the closed loop poles are going to follow the root locus branches. So we'll get one kind of there. We'll get one way the hell out there. And we'll get one kind of on these root locus branches, and they are these asymptotes. And these asymptotes go off the page, but the idea is that this asymptote crosses into the right half plane. So for very large k, we get one super duper fast closed loop pole, and that's this one. And we get one closed loop pole that's just about canceled. It cancels with a 0. And that's this one. But those two are kind of inconsequential because guess what? We've got 2 right half plane poles. Wow, this is not a good day for the pen. Okay, and this was kind of like just a binary check. When k is small, when k is large, the more experience you have with these diagrams, the more intricate and the more cases you can kind of build up. But I think that at this point, we are safe to say that the system will be stable for low gains and unstable for high gains. Does anyone need help seeing that again?
Yes, please.
So what part of that did you not understand?
In general, I want you to repeat, like.
So this diagram is going to tell us the location, the possible locations of closed loop poles as a parameter in the open loop transfer function varies, in this case, the open loop gain. And what these red branches represent are those possible closed loop pole locations. Now, this is just one branch, so this is just one closed loop pole location. This is another branch, and there is a third and fourth branch that we have this glimpse of it, and we have this glimpse of it, and we don't know how they get from there to there. And then likewise down here, we have this glimpse, and we have this glimpse, and we don't know how it goes from there to there. But these glimpses are enough to tell me that when k is small, we'll have poles kind of near the blue boxes, and when k is large, we'll have poles that have traveled very, very far along these branches. So these branches are also directed insofar as there are motion of the closed loop poles as k grows. Okay, so these are you commonly see arrowheads on these branches telling us the direction of travel. Direction of travel as k grows. And so it just so happens in this particular example that the asymptotes, even though their center of mass is in the left half plane, the asymptotes will cross into the right half plane because these angles are acute. Therefore, because the closed loop pole branches, because two of the closed loop pole branches are going to approach these asymptotes, we know that those branches have to cross into the right half plane, which tells me at large gains, the system is unstable. So that brings me to the next point of analysis, and that is we are also able to compute the exact location of the crossings. Now, this is only relevant if there are crossings, but in our example, there must be crossings. And I'm talking about crossings as when these branches cross from the left half plane to the right half plane. So we're going to be solving for this location. We know that any S that satisfies 1 plus L of S equals 0 is a closed loop pole. That's a consequence of the definition of our open loop transfer function. And we know that if we're solving for a crossing, say if this is our test point, S hat, that S hat has a specific form. In particular, it has no real part. Right? If this is on the imaginary axis, then that's the same, it's synonymous with saying 0 plus some j omega, where this is the height omega. Okay, so this is where we get into this idea that we're trying to solve for L of j omega equals -1. This will tell me all those points on the imaginary axis that can be closed loop poles. An equivalent way of doing this, if you want to practice your Routh skills, is to solve the Routh array and find where the first half, when the left-hand column equals 0. That will also tell you the crossover points. So let's, I think this is new, so let's explore this method. So, chat, what do you think? Yeah, so the question in chat is, for big K, does that mean we have a dominant pole that makes the system unstable? Yes, that's actually right. The dominant pole, actually plural, dominant poles, will be these two that go into the right half plane. Right, because unstable poles will have to dominate stable poles. because a stable pole will give rise to a decaying mode, and an unstable poles will give rise to a growing mode. And so the growing mode will always outweigh the decaying mode. So yeah, we'll definitely get dominant pole behavior, especially when the closed loop poles cross into the right half plane. So yeah, this kind of leading question up here on this slide is meant to get you to think about, because I've squished the diagram now, so I don't have to run into the title, that these branches that we saw for just a couple minutes ago, they have to get in line with these asymptotes, which means that eventually we're going to have behavior kind of like that. And so the only way to get from here to there is to cross this axis. And this question is just to get you to think, like, do you need to even do this procedure? Because this procedure is actually quite long and drawn out. And if you can argue that you don't have to do it, like if your asymptotes never go into the right half plane, then don't do it, because it's kind of a pain. But we should do it because we have this behavior, this situation where a branch starts on the left and has to get to the right, therefore it must cross. So we are going to solve this. I'll go to black. It's a little bit less aggressive, I think. Okay, so we are trying to solve the following equation. It starts off harmless enough, right? We're just trying to find the omega that makes that true. This couldn't be simpler, except that our L function is kind of heinous. J omega plus 2. Oh, this is not a good time to lag. We've got a lot of writing to do. J omega plus 1, J omega plus 3, J omega plus 1 plus J, J omega plus 1 minus J. And that, we're trying to solve for the omega that makes that fraction -1. Now that's fine, but I hope that you'll see that there are two unknowns in this equation. There is the omega, that's certainly unknown, but there's also the k, and that's actually what makes me want to talk about this situation. Because how are we ever going to solve for two unknowns with only one equation? I want you to keep that question in the back of your minds. In the meantime, I'm going to do a bunch of foiling, and you know what? Actually, I'm not going to force you to watch all this. I'm going to skip ahead to if we get k times j omega plus 2 on the left, and on the right, we're going to get a bunch of terms, and there are going to be sums that are real, so -6 plus 5 omega squared, minus omega to the 4 plus 8 omega squared, and then plus j times the following. So -4 omega times 2 minus omega to the 2 minus 2 omega times 3 minus omega squared. Okay, so what I just leapt through is a whole bunch of foiling and expanding these factors back into their original polynomials. But here at the end of the day, we have one equality and two unknowns. So there's just one equality, but k is unknown and omega is unknown. And so I actually want to open this up to the class. What do you think we should do? This is solvable. Any ideas?
Is it solved for the imaginary and the real?
That's exactly right. I think a lot of people are afraid of these complex expressions, but they're actually a real blessing, because the only way for this number to be equal to the right-hand side is if the real part of this number is equal to the real part of the right-hand side. So the real parts of the left and right have to match. So, and then analogously, the imaginary parts of the left and right have to match. So this gives us 2k on the left, and the real bits are just this kind of first half line. So this is minus 6 plus 13 omega squared minus omega to the 4. That is one equation, but two unknowns. But we have a second equation, and that is the imaginary bits to the left, k omega, have to match the imaginary bits on the right. So this is what minus, I just wrote it out. That's a 3, and that's an omega. Okay, so all of a sudden, from one equation, we have manufactured two equations, and that's because there's no way that the real parts can help with the imaginary parts and vice versa. So they have to both be satisfied independently. So now we've manufactured two equations with two unknowns. These are not a linear system of equations. In fact, we have things like powers to the 4, but we can still solve for one, say by substitution, et cetera, et cetera. So if you were to solve this system, I don't think, yeah. So I guess we can just go through this and say that, I'm going to just say dot, dot, dot. If you solve this system, there are 4 possible omegas that solve the system, right? Because there's a 4th order in omega. So omega has to live in either plus or minus 2.28 or plus or minus 2.05j. Okay, so this 4th order polynomial in omega is true, or this system is satisfied with any of these 4 omega values. And if you were to pick this pair of omega values, I think you'll get k of, well, I mean, we can work it out actually. Let's do it here. So 2.28, oh no, I'm not gonna be able to do that. Give me the calculator. Okay, so 2.28, nope. There's 2.28 to the 4, and if I negative that, subtract 6 off of that, and then add, so we're gonna add quantity, 13 times 2.28, and again, close parenthesis, equals, and then I want to divide that by 2. So this gives me a k of about 27. So let me run through which of these 4 solutions are valid. And it's a little bit, I think it's a little tricky. And that's just because we're looking for imaginary axis crossings. So I think many of you might want to pick this one. And that's not right, because remember, the omega that we defined has to be a real number, because the omega is multiplying a j. So that's why I'm focusing my attention on both of these solutions. And it's not surprising that we get a pair of numbers, 2.28 and negative 2.28, because we expect 2 crossings. We expect one here, and we expect one here. And we also expect them to be symmetric. So the fact that they're in plus or minus is exactly what we want. So this is the point 2.28j, and this is the point negative 2.28j. Now the fact that k equals 27 at these points is just kind of gravy. It tells us that for k's less than 27, we're going to be stable, and for k's greater than 27, the system will be unstable. So this one you're going to ignore because omega is real. Even though this statement might be a little confusing because we're looking for an imaginary axis crossing, but the imaginary part of j omega is just omega, so that makes it a real number. Questions?
Could you say one more time how we know omega has to be real?
Sure. So at the get-go, we did something like this. L of j omega equals -1. Now, if you're going to plug in a number j omega into a function, I guess I kind of skipped over this, but you're plugging in an imaginary number. And to get an imaginary number, you take the imaginary unit and you multiply by a real number. And so that's the argument for why the solutions that we're looking for have to be real numbers. Because the actual thing that we're plugging into the open loop transfer function needs to be imaginary. Therefore, if I'm entering in j times a number and I want it to be imaginary, that number has to be real.
Okay.
And the question in chat is, that's the max k value in order for the system to be stable? That's exactly right. So what we've got here are called imaginary axis crossings. And so what we've shown is that when k is equal to this number, then there are closed loop poles on the imaginary axis. And this is the cusp between stability and instability. If k were any larger, then we know that the closed loop poles are going to be closer to their asymptotes. If k were any smaller, then we know the closed loop poles will be closer to their birthplace, or these open loop poles. So that argument means that if I, like 27, or whatever this number is, I have my doubts about whether I calculated that correctly, whatever the k is that gives you this omega is the stability crossover gain. This is our, I think it's our fifth peak, our fifth little view into the behavior of this really complicated polynomial. So we get the behavior, what happens when k is very small. We get the behavior, what happens when there are roots that are purely imaginary. And we get the behavior, what happens when k gets very, very large. And what we don't know is exactly how it gets from A to B to C. Now there is one more step in the root locus procedure that I'd like to show you. And this is determining when and if the branches break away from the real axis or potentially break into the real axis. So the bullet points here give you the most of the story, is that if we ever have a situation, say like this, then if you do your real axis loci parity check, you'll find that the locations closed loop poles can be that are real are between these two open loop poles. And the arrowheads would draw this way. But these closed loop poles have to eventually break off. And that's because there are no open loop zeros in this situation. So we need the branches to go to infinity. And if you work out the asymptotes, you also get plus or minus 90 degrees. And so now the question is, we have closed loop poles that are real for low k and are complex for high k. Where is the transition point? Where is what's called the breakaway point? And analogously, if you had a pair of open loop zeros that were neighbors on the real axis, you actually have the same result, except the arrowheads all point the other way. So now the closed loop poles have to come from off the page and travel towards these open loop zeros. And so what this slide presents is how to calculate this break away or break in points. There are other scenarios where this is relevant that are not just pairs of x's and pairs of o's. And this procedure will actually show you when and if you ever need to do this. The derivation comes from doing a bunch of product rule in calculus, which is why this has the flavor of a quotient rule, right? This is low d high minus high d low. And if I'm trying to set that equal to 0, all the s's that satisfy this will be either break in or break away. And you have to have some context awareness to know whether they're going to be break in or break away. What are d and what are n? They're simply the numerator and denominator of the open loop transfer function, but with k split off. Okay, so there should be no k's in this quotient rule. Okay, and if you're looking for the proof of why this works, I'll refer you to my supplementary chapter on polylearn. So let's see how this is applied to our running example. Now, based on what we have so far in the root locus diagram, I don't expect there to be any breakpoints, but this is still a good test just to make double sure. So what are we looking at here? We're looking at a numerator transfer function that's just s plus 2. Remember, we're excluding the k in this formulation, and a denominator transfer function, a denominator of the open loop transfer function that is the product of s plus 1, s plus 3, and then the two complex conjugate poles. And I have simplified that a little bit. So here's s plus 1 times s plus 3, and here is the polynomial that gives us the two complex conjugate poles. And then this rule says we also need the derivatives of all these, but let's FOIL this out a bit. I've done this ahead of time, so we can skip to the good stuff. 6s to the third plus 13s squared plus 14s plus 6. Okay, so then we can differentiate. So take dds of the numerator and we get 1, and then take dds of capital D of s, and you get 4s to the 3 plus 18s squared, double the 13 to 26, and drop the s. Okay. And so again, the test that we're trying to run is the numerator times the derivative of the denominator minus the denominator times the derivative of the numerator. All right, so let's do this out. We got s plus 2, and then we do times 4s to the 3, 18s squared, 26s plus 14, minus the denominator, s to the 4 plus 6s to the 3 plus 13s squared, 14s and 6, don't forget to wrap that, times the derivative of the numerator, which was just 1. All right, so we're trying to solve for the s's that make that expression equal to 0. And if we can find any valid s's that make that true, then those s's have to be our breakpoints. However, as you'll notice, this is a fourth order polynomial, so it will have 4 roots. The question is whether any of them are valid. And so this gets us to the realm of when is it okay to use a calculator or automated root finding algorithm. And in my opinion, when you have a polynomial with all constant coefficients, you should go ahead and use the tools available to you, because those really are, they can't be beat. And so what I want to do is share with you how I would use MATLAB to find the roots of this expression. Okay, so the polynomial that I want to find the roots of is the product of s plus 2 with the derivative of the denominator minus the denominator times 1. So in MATLAB speak, we need to represent these polynomials with arrays of polynomial coefficients. And so the way to do that when you're multiplying two polynomials is to convolve the arrays that hold those coefficients. So we are going to say the first term in that polynomial is the convolution of s plus 2 with 4s to the 3, 18s squared, 26s, 14s to the zeros. And so that will be, it should have 5 elements in it because it's a fourth order polynomial, and they count down. These are the s to the 4s, to the 3s, to the 2s, to the 1s, and then to the zeros. And the second term in the polynomial was s to the 4, 6s to the 3, 13s squared, 14s's, and 6s to the zeros. Also a fourth order polynomial, and then we're going to subtract them. So p is p1 minus p2, because we subtract corresponding powers of s, and then I can get the roots of p using the roots command in MATLAB. All right, so MATLAB tells us that the solutions to that equation are complex numbers. And the reason that that is evidence that there are no breakpoints is because we defined our breakpoints to be breakpoints from the real axis, which means that the solutions need to be real if they're going to be a valid breakaway or break-in point. And so this is my argument for why there are going to be no break-in or breakaway points from the real axis, because the only points that satisfy the break-in, breakaway rule are complex numbers. They're not real numbers. Okay, so that suggests to me that because the solutions are strictly complex, this means that there are no real breakpoints. Okay, so we introduce this as a way to find the breakpoints. It's also a way to find that there aren't any breakpoints. That's convenient. Questions on that?
Can you describe what exactly occurs at the breakpoint?
Sure. So I'll zoom in on the picture that I had before. Actually, you know what? Let's just do a different example. Let's look at L of S is say K over S and S plus 2. Yeah, so this is a super simple root locus. We've got an open loop hole at the origin. We've got an open loop hole at -2. And the only part of the real axis that is in this root locus is this region. You could confirm this yourself if you drag your pen from right to left and count when you have an odd number of open loop holes to the right. You would only answer yes within this shaded region. So let's solve the breakpoints here. So here, in this kind of sub-example, the numerator is 1. The denominator is s squared plus 2s. Now, if you're thinking that I messed this up because the numerator is k, I want to remind you that we defined n and d on the previous slide by factoring the k out. Okay. So I'm prone to screw a lot of this up, but I didn't screw that up. The derivative of n, so this d derivative gets us 0, and the derivative of big D is 2s plus 2. Okay, so let's do the quotient rule. We're taking n times derivative of d, that's 2s plus 2, minus d times derivative of n, which is 0. Set that equal to 0, and s is -1. Only one solution here because it's first order polynomial. And the reason I picked this is because I can solve this polynomial without resorting to MATLAB, but also because it has a very unique meaning, or like a valuable meaning here, is we have just solved that the closed loop holes, once they get to -1, they hit each other. I like to think of it. I like to think of it as a head-on collision. So the poles are moving this way and that way as k increases. And once they get to -1, they actually smack headlong into each other and bounce off the real axis out into imaginary land. So this location, this -1, is what we solved for. And this is the point on the real axis where the root locus branches hit and force themselves off into the non-real part of the complex plane. Does that help?
Do we know direction-wise? But you said that was based on context.
So the context here is that we have open loop pole, open loop pole. Therefore, these arrowheads always point away from the open loop poles, and so we have a head-on collision and then a breakaway. If, in fact, there's nothing algebraically that would change if we had this system, open loop 0, open loop 0. In this situation, the roles of n and d would exactly flip-flop, and so we would get the same solution at -1, but this time the arrowheads point towards open loop zeros. And so the context here would be, this is a break-in because these branches would be coming from complex land and breaking onto the real axis and then traveling to their respective open loop 0 homes.
can we just assume that they traveled like directly on that line, or
So what's missing from this is the asymptote analysis. In fact, when you have a second order system like this or a second order system like this, they'll actually always travel directly north-south. But in truth, what we're finding here with this breakpoint is just, again, the behavior very close to the axis here. So if we had no other context, all I can say is that the branches will intersect at this point, and then they'll do something, either break in or break away, and then I don't actually know what they do after that. I was working ahead, I guess, because both of these have 90-degree asymptotes. Okay, we got to end there, but I will wrap up. It's kind of an awkward ending because the conclusion will have to happen at the beginning of next class. Good questions. I really do encourage you, check out the textbook, check out my supplementary material online on PolyLearn, because yeah, this is a lot to take in, especially having never done this before. So I will see you on Wednesday.